And if we go back to the original differential equation, this is general form of differential equation like this, where the right-hand side is no longer a U signal. It contains the linear combinations of fractional differentiations of U signal. So what we can do about this equation, since we have talked already about the GL definition computation to a signal, so we have to apply the GLF DIFF function we defined earlier to find the right-hand side of the equation and denote that the right-hand side is given like this. And the right-hand side, it becomes a signal. So we can solve the general form of the differential equation. So in this case, where we can introduce a method which can be used to solve the general form of fractional differential equations. There isn't any limitations on commensurate orders or the signal impulse or step signal. It can be of any signal. So by the use of this method, we can easily find the time domain solutions to given systems. And there are also limitations, as I said earlier, that the U signal must be given first, and it cannot be used inside a system where the U signal is not given. So this one can be used to solve. This one can be used to solve standalone differential equations, but cannot simulate a fractional order system of closed loop because the U signal is not given previously. So there are limitations. And based on this kind of algorithm, I have developed and defined a Matlab function, L, sim, and step function, which are quite similar to the functions in the control system toolbox, and I will explain that one later to you. So with the use of these functions, we can easily find numerical solutions to fractional order systems driven by any signal. So now let's consider the stability analysis of given fractional order systems. And up to now, the stability analysis of the system applies only to commensurate order systems. Denominator should be in commensurate order. Well, if we introduce lambda, which equals to s to the power of alpha, then the characteristic equation of the system can be written like this. And it is an integer order polynomial, so we can easily find all the poles of the system. And another important factor is alpha. So the impulse response of the system can be written like this. Well, these are the poles of the system, and these are the numerical values of the system. So if we express it in partial fraction expansion, we can get the result like this. And from the result, we can see that if all the poles of this equation are distributed in this part, there isn't any pole within this area where there is alpha here. So if there isn't a pole is located in this area, we will say the system is stable. Otherwise, it is unstable. So the alpha is quite important. If alpha equals to 1, we see that this one, lambda equals to s, and it is an integer order system. And for integer order system, when alpha equals to 1, this line will be changed to vertical lines, and which is the imaginary axis. If all the poles are on the left-hand side, it is stable, otherwise it is not stable. However, for integer order systems, we must use a line like this to distinguish the stability regions. So this is the stability analysis of the system. And based on this part, I've written a Matlab function called isStable to check whether the system is stable or not. If it is stable, then the value of k returned will be 1, otherwise it's returned 0. And this is the alpha, which is, I will explain that one later to you, because it is slightly different from the one I used earlier in the presentation. So these are the code I use to check the stability of the system.